Okay, in this screencast we're going to continue our review of sequences and series. We're going to move into the areas of finding the sums now of sequences. When we talk about sums of sequences, we talk about series. So a series is defined as the sum of a sequence. You may have wondered what the difference was between sequences and series. So we'll have a look at series. A sum of a sequence. So a sequence is just, as it suggests there, just a string of numbers. So this is a sequence, 2, 4, 6, 8. A series is 2 plus 4 plus 6 plus 8. That's the difference. Okay. So firstly, let's have a look at sigma notation. So often sigma notation, which is this guy here, that big Greek letter. It's capital sigma. Sigma notation is used for representing arithmetic or geometric series. So remember, a series is a sum. Okay. So with sigma notation, so let's just have firstly, what does it mean? E.g., so what the instruction here would be is to calculate. Let's say we're going from n equals 1 to 5 of 2n plus 3. Now the first thing to note here is that if this is a linear function here, a linear expression, so if this is linear, then what we're going to get, what we're going to find in a second, is that we have an arithmetic. Linear equals arithmetic. Let's have a look. So how do we decode this? Well, we say that what we do is we put n equals 1 to 5. So we're going to have 5 terms here. So what we do is we make 5 separate terms, and we evaluate this expression 2n plus 3 at n equals 1, at n equals 2, at 3, at 4, all the way to 5, and then the sigma bit of it tells us to sum those terms. So let's go and do that. 2 times 1 is 2 plus 3 is 5. So I just put n equals 1 in there, just in case you missed that. That's n equals 1. So what I did was 2 times 1 plus 3. Okay, hopefully that's enough of that. Now if I put n equals 2 in here, I get 2 times 2 is 4 plus 3 is 7. And I plus, because the plus is the sigma. Okay, then I go n equals 3, which is, how am I going? 6 plus 3 is 9. N equals 4, I'll pretend I don't know what's going on. 5 is 13, and oh, look at that. I've got a nice little sequence. 7 minus 5 is 2. 9 minus 7 is 2, so I'm subtracting here. So I've got a common difference of 2, and let's have a look here at the coefficient of the n. It's 2. So that will be, so not only do I see a linear here and say arithmetic, I see the coefficient of the n or the r or whatever letters being used. I see the coefficient as my d. Okay, that's going to be useful. Okay, so how do we calculate it? Well, we'll come back to how to calculate it in a minute. I mean, we could do that manually. That wouldn't be difficult, but when it gets to n equals 1 to 500, it gets a little out of hand. So 5, 12, 21, 32, 45, we can do that manually, but we'll come back and have a look how we're going to use something smarter for that. I want to do a geometric, so I'm going to do n equals 1 to 4. Now a geometric looks like this, 2 to the power of n. Let's just go with 2 to the power of n. So where that's a linear expression gives us arithmetic, an exponential expression, which is what we've got there. We've got n in the power, it's an exponential expression, that's going to equal a geometric series. Let's look at how this works. If we put n equals 1 in here, we get 2. If we put n equals 2 in there, we get 4, and we're summing them because of the sigma. The sigma says take the sum. N equals 3 in there, 8. Put n equals 4 in there, 2 to the 4 is 16. Have a look at what's going on here. 4 divided by 2. So dividing by, dividing by, we get the same each time. So r equals 2, and let's go in here, r equals 2. Right, so not only does the exponential tell us that it's going to be geometric, the base, the value of the base here, the 2, gives us the common ratio. Right, well that's really useful, isn't it? And we can add that up. It's not difficult either. 2, 6, 14, 30. Okay, we're going to work out some ways to calculate sums using formulae because I've used small numbers here. Okay, the formula for an arithmetic. I'm just going to give you the formula. Now we can derive these. In fact, it's quite good fun for arithmetics. It's quite quick, but I'm going to give you the form. We've done it in class. We just need to crack on with it. It's 6.5 minutes into the video, and you've got stuff to do. So, an arithmetic sum. Just pick my color out here. Arithmetic. So an arithmetic series. I don't know what just happened there. I hit the wrong button, didn't I? Okay, get me out of here. Get me out of here. That was an extraordinary performance. Let's go back to the start menu, desktop, arithmetic. Let's just be careful what I hit here. Arithmetic series. We call that. We give it Sn, representing the sum of n terms. So I'll just make a note of that. Sn, sum of first n terms. Right, Sn for an arithmetic equals, now it's n over 2. Now it's either, if we know what the last term is, we can just go u1 plus un. u1 being the first term. This is the first term. And un being the last term in the sequence. Now sometimes that's a really nice and quick and easy formula to use. Most often probably we don't have quite such convenient information, so we have to convert this un into u1, so take un and write it as u1 plus n minus 1d, which we know from the previous work on finding the nth term of an arithmetic. So we are actually in effect, and I'm going to pull this back. So this turns out to be 2u1 plus n minus 1d. So rather than write too much down here, I just want a nice trim set of notes for you. So it's going to be 2u1 plus n minus 1 times d as our arithmetic series formula, and our geometric series, we're going to sum that by taking our first term, common ratio to the power of n minus 1 over r minus 1. That can be written the other way around, not to confuse you, but we can write this as just by multiplying top and bottom by minus 1. And I'm just going to write this because you sometimes find it useful to write it in this form. So it's essentially u1 by r to the n minus 1 over r minus 1, or we can switch it around. That's how we find our geometric series and our arithmetic series. Okay, I'm going to go and do some questions in a moment, but there is a situation where we're able to find the infinite or converging sum, of a geometric series. Now this is for, importantly, for r between -1 and 1 only. So this is the series that goes 9 plus 3 plus a third. See what's happening here? Our ratio is 3 divided by 9 is 1/3. 1/3 divided by, what happened there? I missed one. I missed a term. Sorry, I missed 1. So we're dividing by 3 each time. Now we're back on track. And you can see that our common ratio here is 1/3. So when our ratio is between -1 and 1, so it's fractional, what is happening are our terms are getting really small. You can see before I get to the end of this page, if my arithmetic doesn't let me down, is look at the size of this fraction. It's becoming ridiculously small already. Now think 20, 30, 100, 200, 1,000, 10,000 terms into this sequence. Unbelievably, stupidly small. So what we get is a sum. Right, if we're going to sum these terms, right, what do we got? We got 9, 12, 13, 13 and a third, 13 and a bit more than a third, and we're getting so like all these numbers here are not going to get us any more than 1. So we get 9, 12, 13. We're not going to get this. This will converge on 1. So our sequence will sum to 14. So it's called a converging or an infinite sum, and it only refers to geometric series where the common ratio is between -1 and 1. So let's have a look at how the formula for that. What we do is that we work out that this value here, r to the n, if r's a fraction, if r's one of these values, and n's getting ridiculously large, so that's what we're looking at here, because we're looking at the sum of an infinitely large number of terms, this goes to 0. So we end up with 1 minus 0. This just turns out to be 1, this bracket. So we end up with a formula. It's just the first term, u1 over 1 minus r. So we call that the infinite sum. So we look at it like this: n equals infinity equals u1 over 1 minus r. That's a nice one, but we've just got to make sure we're only using it for values of r between -1 and 1. Okay, let's go and have a look at some questions that we can do now. Back up to the top of the exam, because I think we missed a couple out. There's a sum question. Might be a sum question here at the top. Yeah, the sum of the first 35 terms. Let's go back to our arithmetic, where u1 was 3. So we're going to do part C now. Remember, u1 is equal to 3, and our difference was equal to 9. Now our arithmetic, so we want the sum of the first 35 terms, so we go S35 equals, it's an arithmetic, so it's 35 over 2, what are we saying, 2u1, so 6, plus, remember we're using the formula we just came up with, 2u1 plus n minus 1, 8, times the difference, sorry, n minus 1 is 2, what am I doing? Where's that eraser? Where are you? Here somewhere, there you are. So n minus 1 is 2 times 9. So it's 35 over 2 by 24. 2 9s are 18 plus 6 is 24. 7.5 times 24. Quick little duck in here, 17.5 times 24 is 420. So we duck back in, that's our sum, 420. Let's have a look at the sum, no, not there, question 3. We'll come back to question 3, that's an interesting one. The sum of the first 12 of this geometric. So we found the 10th term, but the sum of the first 12 terms is going to be quite large. So remember, u1 is 3, our ratio is 3, so our sum of the first 12 is u1, which is 3, by r's 3, so 3 to the power of n, which is 12, minus 1 over 3 minus 1. Okay, so 3 minus 1, that's r minus 1 there. So that's 3 by 3 to the 12 minus 1 over 2. We need to go back in here and calculate 3 by bracket 3 to the power of 12. It's going to be a large number. 3 to the power of 12 minus 1. So I'm going to take that value and then I'm going to divide it by 2. So I get 797160. Hopefully that's right. 797160. Large sums with these geometrics. Okay, let's have a look at, hopefully there'll be an infinite sum. The sum of the first 25 terms, whose 7th term is minus 247 and whose 18th term is minus 49. So what happens a lot here, we now start to have to use simultaneous equations in order to find out our first term and our common difference. So just have a look at question 3. 7th term is minus 247. So what we need to write here, U7 is 247. This is an arithmetic sequence. So how does this look? Minus 247 equals U1. I don't know what U1 is. I know it's my 7th term, so n minus 1 is 6. U1 plus 6d is that. 18th term is minus 49. So minus 49, if you like, so just to keep consistent here, I'm writing this as now my U18 is minus 49. So that looks like minus 49 equals U1, I don't know what that is, plus 17 times d. So now what I'll do is I've got equation 1, equation 2, I'm going to solve simultaneously. It'll be quite easy because I've got U1s there, I can just do a subtraction. So if I take this here and I subtract, so what I'll do is I'll write this one underneath, minus 49 equals U1 plus 17d. Actually, I might go the other way. How am I going? So I might get rid of, yeah, here we go. Beg your pardon. So I'll write minus 247 equals U1 plus 6d, and I'll do a subtraction here. So I'm solving simultaneously. This is equation 1, this is equation 2, 1 minus 2. Minus 49 minus 247. So that is, so minus 49 plus 247, which is 202, I believe. U1s will subtract, and 17 minus 6 is 11d. So 202 divided by 11, 202 divided by 11, hit enter, control enter, 18.36, did I get that? Minus 49 plus 247, right? I'm going to check that, minus 49 plus 247. 198. So that's 198 there. My mistake on that one. So this is 198. So 198 divided by 11 rather. 198 divided by 11. And you've got 18. So D is equal to 18. And then we can work out our first term by putting that value of D in here, 6 times 18, so U1 is equal to, well, it might be easier on this one, U1 is equal to minus 49, putting it back in, plus 17 times 18. No, it's not easier on that one, but so U1 is equal to minus 49 plus 17 times 18, minus 49 plus 17 times 18, and we get 257 as our U1. 257. So now we can find this, the sum of the first 25 terms. I'll change my color pen here. So S25 will equal 25 over 2. That's n over 2. My first term twice the first term, which is 514. plus n minus 1, 24 times the common difference, which is 18. So we work that out using our calculator. 25 over 2, 25 divided by 2 times, open your bracket up, what do you say we're looking at? 514 plus 24 by 18. 514 plus 24 times 18. Hit enter. 11825 is our result. 11825. Hopefully the sums are okay on that. And that solves that rather big problem there. Only 3 marks. Quite a bit of work to do to get those 3 marks. Okay, I'm on to the final straight here. I'd just like to find an infinite. Here we go. Show that the infinite geometric series 14 thirds plus 4 thirds is convergent and find its sum. So the important thing here with this question, show that it's convergent. Show that this is convergent. Well, we can do that by doing 4 thirds, showing that 4 thirds divided by 14 thirds, and working that out, we can see that that's 4 over 14 or 2/7, and then showing that 8 over 21 divided by 4 thirds gets us the same result. That's also 2/3, 2/7, sorry. So then we can conclude that this is a geometric series where r is equal to 2 over 7, and therefore converges. It converges. It has an infinite sum because the value of r is between -1 and 1, as r is between -1 and 1. So we can find this sum now. Go ahead and find it. First is u1, 14 thirds, over 1 minus 2/7, which is 5/7. So 14 thirds divided by 5/7, and that's, yeah, sorry, 14 thirds, come on, I'll get rid of that window. 14 thirds, okay, just doing the calculation, 14 thirds divided by 5/7, and that is 98/15, and we just put that in here, and that is our converging sum, our infinite geometric sum. Okay, I'll close there. Good luck with it all. Cheers.